Hi everyone. In this talk, we'll talk about instability in constraint reinforcement learning and a solution to it based on recursive constraints. The problem we consider in this talk is optimizing a Markov decision process on the safety constraint, which is defined by a probabilistic reachability of a set of failure states being less than or equal to a given threshold. Specifically, we try to find a policy that is deterministic and uniformly constrained optimal, meaning that in every state, an agent should choose a safe optimal action, or if no safe action exists, the least unsafe action. This problem arises naturally in safety critical systems such as autonomous driving, where it is required to maximize performance while bounding the probability of hazards in all states. However, although it is intuitively simple and similar to the other problems, this definition appears not to have an adequate existing solution. In this work, our main focus is to show instability issue when using the idea of reinforcement learning in solving such a problem. We also show that such an instability issue can be solved by our proposed idea of recursive constraints. So, let me first introduce the underlying finite Markov decision process, which is defined by a tuple where S plus is a finite state space consisting of the set of all non-terminal states S and the set of all terminal states S perpendicular. And A plus is a finite set of all actions, which defines the set of all actions available from each state S. T of SA defines the next state distribution given action A available in each non-terminal state S. Gamma is the discount rate, and the reward model R defines the reward for each transition and at each terminal state action pair. Since we consider deterministic policies not stochastic ones, we define a policy as a mapping from state space to the action space such that it outputs an available action for each state. Given a state S or a state action SA, policy pi of an MDP generates alternating sequences of states, actions, and rewards, as you can see here, where the initial state or initial state action is determined by S or SA, and then you follow the policy thereafter, with the next states and the rewards generated by T and the reward model R like this until a terminal state is reached. T is the terminal index, and such a ruleout is terminated when you reach a terminal state denoted by ST. Then you define the value function and the Q function for the policy pi as the expectation of the cumulative discounted reward, given that you start at state S and state action SA respectively when following the policy pi. We also define probabilistic reachability of failure states as a safety measure where the failure states are given a priori as a subset of terminal states. Given policy pi, the probabilistic reachability of failure states at state S and state action SA is defined like this as the probability for the terminal state being a failure when you start at S and SA respectively. Here the math carpet denotes the Q function for the probabilistic reachability. Then given threshold theta, We partition the state space like this, where S of pi is the safe region defined as the set of all states at which the probabilistic reachability under the policy pi is less than or equal to theta, and the unsafe region F contains all the other remaining states. Now we define the properties that we want our constraint optimal solution to satisfy. We denote pi hat the assumed existent optimal policy satisfying the properties P1 through P4 that we'll describe, associated with the threshold. And for simplicity, we denote the safe and unsafe regions under that optimal policy like this. Then the first property is uniform optimality. That is, for any policy pi, the optimal policy has a higher value at any state in its safe region only when it is less safe in that state. Likewise, the optimal policy is safer at any state in its unsafe region only when it is less performing in that state. In other words, P1 means that it is Pareto optimal with respect to performance and safety uniformly in its safe and unsafe regions, respectively. We may have multiple optimal policies that all satisfy P1 but achieve different Pareto efficiency. The second property we call second uniform optimality over F hat limits such optimality to the cases where the safety is maximally improved over the unsafe region. This property makes sense also in practice since we trade off safety and performance within the safe region, but not in the unsafe region, in which safety becomes the first priority to be optimized. The third property simply means that we should be able to achieve a better performance when the constraints are weaker. Here we hope but don't claim the existence of such an optimal policy satisfying these three properties and leave it as a future work. Instead, we focus on the next property. Consider the policy relation operator, which takes the policy pi and outputs a policy pi prime that maximizes the Q function among the safe actions on the pi, which we denote A of S on the pi here, and if no safe action exists, it minimizes the reachability. Then our fourth property is that the optimal policy has to be a fixed point of such an operator. This property is reasonable since the operator maximizes the performance in the safe region and minimizes the risk in the unsafe region. It's also necessary for convergence of reinforcement learning. However, we'll show that such a fixed point may not exist, and there's mismatch between the first and these properties. First, we consider this counterexample MDP to show the non-existence of the fixed point. The state space is like this, where S1 and S2 are non-terminal, X and G are terminal, and X is the failure state. There are two actions, left and right, but the left action is not enabled at S2 for simplicity. The probability P determines the transition probabilities of this counter MDP, and we consider the case with P greater than 0.5 only. In this counter MDP, only two policies exist, since you can choose left or right only at state S1. We denote those policies by pi sub L and pi sub R. The reward is -1 for all transitions before reaching a terminal state, and 0 in the terminal states. The discount rate is 0.95. This setting makes the agent minimum time optimal for reaching either the goal or the failure state. Here we investigate those two policies at state 1 only, and simplify the notations by denoting the state action functions at state S1 like this. For example, Q of AR means the value when you choose A at S1 and follow the policy pi R thereafter. Here are the curves of those Q values versus the probability P. And as you can see from the figures, for any policy, choosing L always yields higher Q values than choosing R. On the other hand, from this probabilistic reachability versus P graphs, we can also see that choosing R is always safer than choosing L. The problem is, for example, at this point, where P is 0.7 and the threshold is 0.85. At this point, I'll alternate between being safe and unsafe, depending on which policy to follow after choosing that action. In other words, even when pi sub L is not safe, left at S1 can appear to be safe if we follow the other policy pi sub R. In summary, at this point, choosing L always yields better performance than choosing R, is always riskier than choosing R, and appears to be safe if pi R is followed while pi L is not safe. A consequence is that in this policy iteration that starts with the policy pi R, it chooses pi L alternatively since L appeared to be safe when pi R is followed at the odd number of iterations. So we cannot make the convergence in this case, meaning that the fixed point property doesn't hold. So it is required to choose safe actions more conservatively, as unsafe actions can appear to be safe. Now let's have a close look at the fixed point property. Suppose we are at safe state S satisfying the safety constraint under the optimal policy. Also consider these two constraint action sets under the optimal policy, where A hat is a conservative version of A. Now let's take a look at fixed point property, which implies that the optimal policy must satisfy this equation at safe state S. And that is equal to this by optimality of the policy. On the other hand, the uniform optimality P1 implies that at safe state S, it is Pareto optimal in this sense, which means that the optimal policy has to satisfy this. But since there might be an action that is outside A hat and has a higher Q value, while appearing to be still safe, the same equality doesn't hold in this case. Therefore, the implication is that P1 does not necessarily imply P4. And we hypothesize that the safe action set in P4 has to be more conservative, which is at least true for the count MDP. So let's now revisit the count MDP with the idea of recursive constraints. The counter MDP had this oscillation problem in running policy iteration. And the idea of recursive constraints is to define the constraint recursively over the axis. For example, the recursive constraint for choosing action L at iteration 1 is the same as that in the table, but at iteration 2, We define the recursive constraints as a conjunction of the constraints at iterations 1 and 2, which we can write like this explicitly. And the same goes for the iteration 3, iteration 4, and on and on. Thanks to the recursive constraint, we can now see that the oscillation in policy iteration doesn't happen as the previous constraints come into play. So, we'd like to extend this motivational idea to other dynamic programming and reinforcement learning methods such as value iteration and Q-learning. But except for policy iteration, initial or early estimates of the probabilities are typically random and has no reliable information. And those inaccurate random constraints will be transferred to all later iterations, messing up the constraints all the way to the end. So we provide two solutions to this. One is to replace the axis of iteration with the axis of horizon of probabilistic reachability. Then we modify the constraints at stage n in state S like this, where this math car Pn is or over approximates n-bounded probabilistic reachability. This n-bounded probabilistic reachability is not the same as unbounded probabilistic reachability that we defined earlier. We'd like to mention that this proposed recursive constraint idea is fairly general in that it can be implemented on top of naive algorithms such as naive versions of value iteration, policy iteration, and Q-learning. Here, we consider naive value iteration, which first initializes the P and Q arrays, for example, in this way by using the MDP, and then run k number of iterations where we find the estimated set of all safe actions for each state, and then get the next policy from those constrained action sets and Q and P arrays. The subroutine constructs the policy in the same way in the policy iteration operator. Then by using the obtained policy, naive value iteration updates P and Q arrays where the update rules are derived from the Bellman equations. And then it returns the P and Q arrays as estimates of the Q function and the probabilistic reachability with respect to the policy pi. The value iteration with recursive constraints can be given like this, where we introduce the horizon in the inner loop and returns the estimates of the Q function and an over approximation of the n+1 bounded probabilistic reachability. The major change is that the constraints are now recursively given, which we can see from the update rule of a hat from both a hat and the current constraint shown in the set. And the array Pn in the constraint approximates or over approximates the n-bounded probabilistic reachability. Another major difference is that P array in the next horizon is updated from P array in the current horizon, which serves as a stable target. Regarding the stable target, I'd like to mention that the P1 array is already accurate, so we don't need to update P1 anymore, and each of Pn array is updated only at the previous horizon. Now we show the results of experiments of both naive and proposed value iterations on simple cliff worlds. Our cliff world has the same states as in the counter MDP, but is generalized by allowing actions in all possible directions. Transitions to the desired direction is made with probability 0.5, and to a random direction with the remaining 0.5 probability. Here is the results of naive value iteration after 50 iterations for each threshold on the x-axis. At around theta equal to 0.8, naive value iteration thinks that the current policy is safe in orange curve, while it actually is not in the blue curve. Moreover, the switching between the policies randomly induces errors. Whereas in the value iteration with recursive constraints for 15 iterations with 15 horizon, we see no such shadowing and violations observed. From these graphs, we can clearly see that the solution of our approach for each threshold is apparently stable and converged. In summary, we found the instability issue when using reinforcement learning ideas for finding a policy that is deterministic and uniformly optimal on the safety constraints. And from the investigation, we conclude that our approach with recursive constraints can solve such instability issue in naive approaches. We investigated policy relation with counter MDP and value iteration with cliff wall experiments. We hope this can clarify some hidden problem within multi-objective optimizations, and the future work is to extend the idea to reinforcement learning with functional approximation for more complex tasks. Thank you for watching the video.